In this video, we'll talk about one result about convergence of Taylor series and show how that relates to things we've dealt with previously and how that means we can use some of our previous examples to go forward with this. The question we now want to ask is, when does a Taylor series converge? And in particular, when does it converge to the function f that we start with when doing this process? It doesn't always converge, and even if it converges, it doesn't have to converge to f, and that can be a problem when trying to solve these other situations. However, there's one result that we have to give us a really easy way to figure out when this does happen. Well, the second result later that's more complicated, but here's an easy one we can use. And it's the following. It's that if a function f has a power series expansion, that expansion is the Taylor series for that function, and it converges to the function that we care about. That's the idea. If I already know my function f has a power series expansion, like it looks like 1 over 1 minus x, something like that, where I know I can find the expansion for it, then that expansion is the Taylor series for f, and it converges to f wherever it's valid. So that means that I can do the same sort of arguments that I want to make with a convergent series of functions to this function f, but as long as I have a power series first, that gives me the way in to make this happen. The main point here is to give us some examples to start building from in terms of Taylor series that we know. We knew we had power series before, but now we know these are also Taylor series. And we'll see later why knowing these are Taylor series are also really nice for using them to approximate functions. So as an example, let's verify that the Taylor series for 1 over 1 minus x is the sum from 0 to infinity of x to the n. Now, we know this should be the case because this is the power series expansion for this function. Let's see what we get for this when we start taking derivatives. That's the other way we can define Taylor series, is by taking the derivatives of all these terms and plugging them in to get what the series should be. So my function f of x is 1 over 1 minus x. So f of 0 is 1. That's good because that's the first term in my series. Now if I differentiate, f prime is going to be 1 over 1 minus x squared. I'll get a minus 1 from the minus 1 on the power and a minus 1 from inside, so it's positive there. F prime of 0 is also 1. That's good. F double prime of x is going to be now a 2 over 1 minus x cubed. The minuses and the powers are always going to get canceled out by the minus x I get from the chain rule. So I get a 2 here. So f double prime of 0 is 2, which means f double prime of 0 over 2 factorial is 1. This is also good because all of our coefficients in the series are all 1. So these should all come out to 1 to validate what's going to happen here. We'll do one more step out. Third derivative of x should be 3 times 2 over 1 minus x the fourth. Same idea as before. So f triple prime at 0 is 6, meaning f triple prime at 0 over 3 factorial is still 1. And you can see the pattern here. As I keep going, I'm going to multiply the top by 4, and then 5, and then 6, and then 7. The point being, I will get that f eighth derivative at x is going to be k factorial over 1 minus x to the k plus 1. If I plug in 0, I get k factorial, which tells me f k at 0 over k factorial is 1. And this here holds for all k. So what does that mean? That means the Taylor series for this function, centered at 0, is sum n from 0 to infinity. Nth derivative at 0 over n factorial x to the n is exactly just x to the n because all those coefficients are 1. That's how one would verify that this is actually the same series. You have to compute the series the other way by taking derivatives and see what that gets you for this function. We get the same thing, which is good because we already know that 1 over 1 minus x has this as its power series expansion, so that should be its Taylor series as well. One more example, let's look at the Taylor series for e to the x. We saw before that this is x to the n over n factorial based on the fact that this power series here converges everywhere and is its own derivative, therefore it should be e to the x. Let's now work this out just via normal Taylor series methods by taking derivatives and seeing what we get. So the function itself is just e to the x, so f of 0 is 1. Great. The function's derivative is also e to the x, so its derivative at 0 is also 1. And since it's e to the x, this pattern just keeps going. The derivative is always e to the x, and so every value at 0 is 1. So what does that mean? That means the Taylor series, which is the sum n from 0 to infinity, nth derivative at 0 over n factorial x to the n, well, these here are always 1, so I get sum n from 0 to infinity x to the n over n factorial, just like I should. And now where you could go with this in here is and say, I developed this series now. Now I can show this is actually a power series expansion for e to the x because it converges everywhere. And then that gives me that this works the way it should. That's the idea of our first method for doing convergence of Taylor series. If we know a function has a power series expansion, that is its Taylor series. We can use that going forward, do some arguments with that.